Welcome. This video I'll continue expanding in large aspect ratio of the Grashofanov equation, and this lecture I'm going to introduce show the first order result. So when you go from a cylinder to a torus, what happens when you bend the plasma around into a donut, you end up with this outward shift called the Shafanov shift. In a previous video I went through this from a physical arguments that you get this hoop force from the current and a tire force from the pressure, and that this results in an outward shift of the plasma flux surfaces. In this lecture I'll go through and show you that mathematically from deriving through the Grashofanov equation. And this continues from a previous video where I looked at the large aspect ratio, so cylinder approximation of the Grashofanov equation. And the basic idea is that we have an axis of the machine, we have a plasma, this is at a major radius r0, we have a minor radius r, we have a new toroidal coordinate system where this angle theta, so we have a theta angle going around here, minor radius outwards here, and we can write everything, the whole Grashofanov equation as, so this is the Grashofanov equation written in terms of this cylindrical toroidal coordinate system, and so we end up with these various terms. So there's the right hand side here with the pressure and the current function, and then in the previous video showed that when you go to large aspect ratio, so if you assume that this is a cylinder, so you go to infinite aspect ratio, you end up with the psi, the flux function, writing this as some function of r and theta. I'm going to show that when you write this as a zeroth order term, if it's only a function of r, so it's constant in theta, then you get a solution where essentially all of this disappears. You get a coupling term here with a cos theta, which of course you drop because you're assuming that this goes to 0, and then you end up with an equation for theta naught, which was, so this is an equation just for psi naught. So here p prime is the derivative of pressure with respect to psi naught, for example. And what we'll show this video is that this zeroth order sort of correction, so a zeroth order solution can be corrected. So you can add an extra first order correction, so psi 1, which is a function of r and theta. And what we're going to do here is show what this looks like. So there are various ways of doing this. One motivation here is that if you put this psi naught into this equation, you end up with this term here with a cos theta. We also showed previously that if you what we expect is that the flux surface will be shifted outwards, and this would correspond to a cos theta like perturbation, so moving things radially outwards in r. And finally, if we also look at what this term does, this is an r squared term. So this is, so r is r0 plus r cos theta. And so here we end up with we can expand this out, we end up with an r0 squared plus 2r cos theta plus an r squared cos squared theta. And so we end up with another term involving a cos theta. And so this is one motivation for expecting this psi 1 to be a cos theta kind of dependence. Then we'll end up with some terms which are like cos squared theta, and here we'll have a sort of a sine squared theta, and so that will be a next order of correction. But at least at the next order we're going to look at here, we expect something that looks like cos theta. And so here we're going to write so first order corrections. So again, expect psi 1, which is a function of r and theta, to be some kind of function of r times a cos theta, and call this psi 1 bar, which is the radial dependent part. Okay, next I want to expand these pressure parts and this flux function here. So here we can write p prime of psi. We can do if the correction is small, we can do a Taylor expansion, and so we can write that this is p prime of psi naught, which is what this is here in the current equation here. Sorry, in this part here, in the zeroth order force balance. plus the Taylor expansion, which is p double prime, is the second derivative of p with respect to psi naught, multiplied by the correction, so multiplied by psi 1. So same for ff prime, so ff prime, which is a function of psi, is like ff prime of psi naught plus the derivative of ff prime, so we call it ff prime all prime, times psi 1. Okay, so these will go into this term here. We're going to expand this and keep only the cos theta parts, and then substitute this equation for psi 1 into the Grashofanov equation. And then we're going to keep all the bits that depend on only cos theta. So the zeroth order terms will so from psi naught will all cancel out. We'll get terms involving cos thetas, and then we'll get high order terms involving cos squared thetas. And so for now I'm only going to keep the cos theta terms. And so you get a contribution from here with the psi 1 bar. This second derivative in theta will give a minus cos squared. You'll end up with a derivative here, which we'll see very shortly. So we can write out the whole thing. So here I've written out all the terms, but I haven't written cos theta everywhere because it would just make things a bit more messy. So this term comes from the second derivative in theta. So this term here comes from this term here, where we've got cos theta and d by dr, so with the sine naught goes in here, that gives us d by dr. This term here, these come from the expansion of this, so an r naught squared with a p double prime. Okay, so this comes from the expansion of this r squared as this, multiplied by the expansion of p prime of psi, so here. Okay, so I've got an equation here for psi 1. We're going to need some manipulating this to simplify it a bit. So one thing we can do is just recognize a few terms. So this, for example, is just b theta. So b theta is just the derivative of psi with r and with a 1 over r in front. So it's called b theta. The next thing we can do is try and get rid of some of these derivatives. So we have a d by d psi naught in here, d by d psi naught in these terms here. And so we can try and write this as d by d psi naught, which is each of these primes. We can turn them into d by drs, so radial derivatives. And then this part is just 1 over r b theta. And so this allows us to write p double prime. So that's p double prime part and we can write this so it's ff prime, so we have 1 over r b theta, and then we have this derivative in sine naught becomes a d by dr, or just ff prime. So now we're going to multiply all terms by b theta times r, so multiplied by r times b theta here. So we can just write down what this becomes. So we have, okay, so hopefully it's very clear where this came from. So this term here is just in order on the left hand side. The right hand side group together this second derivative in p and this ff prime. So these two terms here we group together into this d by dr with a p prime and an ff prime. And then we have this term here, which has come from this term up here with the 2 mu naught r in front. And the p prime was a derivative in psi naught, and that has now become a derivative in r, and the b theta has come from this multiplying through by b theta. So the next step is to recognize that this term here in the brackets corresponds to the zero order force balance. So this term, if I can get this on the same screen, I can't, but this is this from the zeroth order force balance. We had this term on the right hand side. We can just substitute in this term. And then this term here, we can do the same substitution as before, and this just becomes R0 times B theta. Okay, so then we can write out this, simplified a bit, because now I'm going to take this part here, so I put this in a box. So I have this component over here. I'm going to try and see how to simplify it. And so I've just taken this part here, having substituted in this expression from the zeroth order force balance, and then you can expand this out and you end up with this term here, and you end up with this term, the B theta divided by R, and that term cancels with this term here. So this term and that term cancel, and so overall we're just left with, if I group this and this term here now on the left hand side. So here the first term has just come from this first term up here, second term has come from this red bit here, so this bit here, went into there. This RB theta squared survives, and this 2 mu naught R squared just comes down here. Okay, then it's not particularly obvious, but this part here can be simplified, and so you can write this whole thing as a d by dr. So you can multiply this out yourself and see that this is true, and this allows us just to write down this in a slightly simpler way. So we end up with the final result for now is, this is an equation for the first order correction, psi 1, in terms of the psi naught quantities, so things like B theta and pressure, and this will give us an equation for the correction, so the radial shift we're expecting. And we can have a look and think about what this means. So for example, here we have RB theta squared. This is always bigger than 0. dP by dr, if pressure is usually decreasing outwards, and so this is usually negative, and so this whole right hand side is always positive. And so we can also consider that this is also positive, this coefficient in here, and so we can just write down that we can plot kind of very roughly what we'd expect this to look like. So if this is R, we can make a plot of what this function here looks like. So since the right hand side is always positive, when we integrate this in R, we're going to end up with something which is kind of increasing the radius. And the exact value will depend on the boundary conditions. Of course, when you integrate this once, you'll get a free parameter you need to determine, and of course determined by the profiles of the pressure and the poloidal field. But we can integrate this again, because we can think about this is also bigger than 0, so we know what sign this should have. And when we integrate this, you'll end up with psi 1 B theta, which kind of looks a bit like this. Again, it's R. So we know that psi 1 of B theta is some increasing function of radius, and the exact value will depend on what boundary conditions we set. So we can see how to interpret the values of psi 1 that we're getting, and what this means. So when you think about what shifted circles would look like, so psi 1 is the perturbation which has been caused by the radial outwards shift of the plasma, and so what we can do is we can write down what psi is. So psi, now some function of r and theta, was the initial cylindrical solution plus the correction, which is this psi 1 bar cos theta. And here psi 1 bar is just a function of r. And so what we've done is we've taken, if we draw our flux surfaces here, So psi1 looks like a set of nested surfaces, so the so-called magnetic axis, which is the center flux surface here where the field line just goes around the machine, is at the geometric axis where r is equal to 0. What's happened is that this has been shifted, and now if you draw the middle of the plasma, so there's a geometric middle, which is here where it was before, and there's the magnetic axis, which is this point over here. So this point here is the magnetic axis. And there's a shift, which is this delta, the Shafarnov shift. And we can think about what the value of psi is here. So if we have a radial shift, then the value of psi on this axis here is the same as the value of psi on this magnetic axis here. And so the value of psi at r, which is now r naught plus this delta, is now equal to the value of psi on the axis of here, of this. This is psi naught. This is all psi naught, and this is psi. So this is psi naught at r naught. So we're essentially mapping from this location to that location by shifting, equivalently going left here a distance delta. So for example, what's happened over here, this value here is the value at the edge of this flux surface here, and so we can write that. So we can write that psi at r is approximately equal to psi naught at r minus delta. So we're taking this value and we're working out from here what the value of psi was by shifting it backwards, this distance delta. So by again doing a Taylor expansion, we can just say that we have some variation in psi. We're shifting it by distance delta in r, and so we just say that we have an original cylindrical equilibrium psi naught. We shift it a distance in r, and so this is the first order correction in the Taylor expansion. And of course this now d psi naught by dr, this is just d psi naught by d little r, because it's the only quantity that psi naught depends on, times dr by d major radius r. And this is just d psi naught by dr times cos theta. So therefore we can recognize that we have psi r theta. This has come from the Taylor expansion, and we can just do the same trick as we've done before and just say that this is equal to r naught times b theta. And then by comparing this to what we've been using, so psi naught plus psi 1 bar times cos theta. So we just recognize that this psi 1 bar is just related to this. Delta r. So therefore I have the psi 1 bar, which is from function of r, is just a minus, so we have a difference of sign here. And if we had, remember the graphs we had before for what psi 1 looked like, so psi 1 is a function of r, so psi 1 divided by b theta here. And this was some kind of increasing quantity with r. We didn't specify what the boundary conditions were, so we just know that it's increasing with radius. And therefore, we can say that the delta, so psi 1 divided by b theta, r naught is always positive, so delta is always decreasing. So we can plot what delta looks like against radius. So it's always going down. Now a sensible boundary condition for delta is that it goes to 0 at the outer edge. So at the outer edge of the plasma, So we specify a flux surface, and so on here we say on this surface delta equals 0, and so psi is equal to psi naught, and the flux surface inside move relative to that outer surface, and so this surface here is when r is equal to a, and so here we define the boundary condition on delta. Similarly, in the core, the common or sensible boundary condition is that the gradient of delta goes to 0. So here we have that d delta by dr equals 0. So here we have delta equals 0, and that's enough for the two boundary conditions we need to specify delta. And then we know it's going down, and it'll typically do something like this. So delta is positive in the core, and that means an outwards shift. So delta is this shift from the axis, the middle, out to here. And this shift decreases as you go radially outwards.